Have you ever looked at a study and thought, wait, that can't be right? Sometimes the most confusing results come down to one simple thing: time. Today we're diving into a really cool statistical tool called survival analysis. It's all about figuring out not just if something happens, but when.
So, let me kick things off with a puzzle. Imagine you're looking at a clinical trial. The group taking a new drug survives for an average of 9 months. The group on the placebo, they last an average of 11 months. So the drug failed, right? I mean, that seems obvious. Well, stick with me, because the answer is way more interesting than you think. To crack a puzzle like that, we first have to talk about the problem of time itself. See, when you're tracking events over time, like patient survival, or even how long a machine will last, there's this hidden little quirk in the data that can make a simple average tell you a complete lie.
And that quirk has a name. It's called censoring. It's what happens when your study ends before you get to see the final outcome for everyone. Think of it like a marathon. Some people finish the race, so you get their time. But what if others move to a new city halfway through? You don't know their final time, but you do know they ran for at least, say, 10 miles. You can't just throw that information away. And that's the genius of survival analysis. It knows how to use that partial information.
So how do we actually handle all this messy, incomplete data and still make sense of it? Well, we start by drawing a picture. And the first tool we're going to pull out of our toolkit is a special kind of graph that does a beautiful job of visualizing survival over time. It's called the Kaplan-Meier curve. To see how this thing actually works in the wild, we're going to follow a real study from New Zealand. Researchers there were trying to figure out the survival rates of young kiwi chicks.
Okay, so this is their first Kaplan-Meier curve. It's showing the survival probability for all the chicks just lumped together over 180 days. You see that steep drop at the beginning, and then it kind of flattens out. But to be honest, this view isn't super useful. It's the same problem as our drug trial. It's just a big, messy average of everybody. The real magic starts when we ask better questions. What if we could actually separate the chicks based on where they lived? How would we compare them then? And boom, here it is. This is what it's all about. The researchers split the data into two groups. That top line, that's the kiwi chicks living in areas treated with poison to kill off predators. The bottom line is the chicks in the untreated areas. All of a sudden, the story is just crystal clear. The chicks in those treated areas are surviving at a much, much higher rate. Let's just quickly break down what we're looking at here. The vertical y-axis, that's your survival probability, from 100% at the top down to 0. The horizontal x-axis is just time passing. Every time you see a line take a step down, that means an event happened. In this case, sadly, a chick died. And what about those little tick marks? Yep, those are our censored data points, the chicks that were still alive when the study wrapped up.
Now, these Kaplan-Meier curves are fantastic for comparing one thing, like treatment versus no treatment. But you know, real life is always more complicated. What if a chick's size or its age also made a difference? To juggle multiple factors all at once, we need a bigger, more powerful tool.
And that tool is the Cox Proportional Hazards Model, or as most people call it, Cox Regression. Just think of this as the heavy-duty workhorse of survival analysis. It lets us throw a bunch of different variables in at the same time, like treatment, age, weight, you name it, and it tells us how each one, on its own, affects the risk of something happening.
The key number you get out of a Cox model is called the hazard ratio, or HR. It's basically a score that tells you if something helps or hurts survival. If the HR is bigger than 1, that factor increases the risk. If it's less than 1, that factor is actually protective. It's that simple.
So let's go all the way back to our drug trial puzzle. How could a drug with a shorter average survival time actually be the better choice? Well, a Cox model could spit out a hazard ratio of, say, 0.72. And what that means is, at any single moment in time, a patient on that drug has a 30% lower risk of dying than someone on the placebo. This can totally happen if, for instance, the sickest patients are the ones who get the new drug. It drags the average down, but the drug is actually helping everyone who takes it. The hazard ratio lets you see right through that confusion.
Now, I know what you're thinking. Running these models sounds crazy complicated. But the cool thing is, modern software does pretty much all of the heavy lifting for you. So let's take a quick peek behind the curtain and see what this actually looks like for a researcher. Generally, the process goes something like this. First, you get your data ready. Turning words like treated or untreated into numbers the computer can understand. Second, you tell the program what's what, which column is time, which column is the outcome, and which groups you want to compare. And finally, you run a statistical test, like something called a log rank test, which basically just asks, is the difference we see between these two curves real, or could it just be random luck? And this is what it looks like inside a program like SPSS. On the left there, you've got the window where you set up the whole analysis, pointing to your time and status variables. Then, on the right, you're telling it to run that log rank test to formally check if the difference between your survival curves is statistically significant. So, after all that analysis, what was the final verdict for our Kiwi chicks? And maybe more importantly, what's the big catch? The crucial warning you need to hear before you ever just blindly trust a result from one of these things. The log rank test came back with this p-value, 0.0034. Now, if you're familiar with statistics, you know the typical cutoff for saying a result is significant is 0.05. This number is way smaller than that. This is a slam dunk, highly significant result.
So the takeaway was absolutely clear. The treatment worked. The researchers concluded that using poison to control predators like stoats and cats made a huge difference in Kiwi chick survival, a difference that far outweighed any other risks.
But, and this is a really big but, here's that catch I mentioned. These tools are incredibly powerful, but they have settings under the hood. And if you don't know what those settings are, you can get yourself into a world of trouble. Just look at this. This is the output from a Cox regression on the exact same data set, but run in two different, very popular programs, SPSS and R. Look at the numbers. They're totally different. Some are even positive in one program and negative in the other. So what gives? Is one of them just completely wrong?
Nope, neither one is wrong. As an expert over on the forum Stack Exchange explained, the entire difference comes down to a default setting. Each program just picked a different group to be the baseline for comparison. So R was basically asking, how is the treatment group different from the untreated group, while SPSS was asking the exact opposite question. The math is the same, but the output looks like a mirror image.
And that brings us right back to where we started. A drug can have a lower average survival time, but still be a lifesaver. A p-value can look amazing, but a simple default setting in the software can flip your results upside down. Survival analysis is an incredible lens for understanding our world, but these tools are only as good as the person using them. So the question you should always be asking isn't just, what did the computer say? It's, do I really truly understand the story my analysis is telling me? Thanks for joining me for this explainer.